Verifying trigonometric identities. All right, so in previous videos, we talked about simplifying trigonometric identities where you're, given an expression and then you just use the Pythagorean reciprocal and quotient identities and get them as simple as possible. Now we're going to do a little bit different of task here. We're going to be given an identity. We're going to be told, hey, this is an identity, which means it's a true statement. This is a true statement as wacky as it looks. And we need to prove that it's true. And in order to do so, we need to be able to start at one side and turn it into the other. Now, if you're doing this on paper, you get the choice of which side you start with and which side you end with. However, using Alex, it's a little bit different because there's a topic that has you verifying identities and you're starting with the left side always. It always has you starting on the left side, which is nice. I mean, makes it so that you don't have to choose which side you start with, but that's how it'll always work with Alex. So that's what we'll be doing. We'll be starting with the left-hand side and moving it into the right-hand side. We'll be using all of these identities up here, and we will be doing the algebra, the verifying by writing down which rule is used at every step of the way. So the steps have been given to us, right? Here's how you get from here to here, but why? Why does it work? Why does this math over here make sense? What identity was used? Was it algebra? Was it one of the identities you know? So either you're using an identity that you know, or you're using algebra. All right, so complete the proofs of the identities by identifying the rule that justifies each step. The rules you use are algebra, reciprocal, quotient, or Pythagorean. Okay, so just a little bit of terminology first of all. If I use LHS, this stands for left-hand side. That's the left-hand side of the equation. So this is the left-hand side. And RHS is right-hand side. I will be using that notation from time to time. All right, so the first statement, sine squared x is minus sine to the fourth x, that is not a rule, that is just what the left-hand side was. That was what the left-hand side was to begin with. To get from this first step down to here, well, looks like to me that a sine squared was factored out. They factored out a sine squared because then I was left with 1 minus sine to the sine squared x. Factoring is just algebra. So that was algebra that was done to get from step 1 to step 2. Line 1 to line 2, rather. All right, so now I'm looking and I'm like, what has happened here? And if things remain lined up, which they don't have to be, but if they did, would it be true that these two things are equal? Is sine squared equal to 1 minus cosine squared? And indeed, it is. So, well, that would be a Pythagorean identity. What happened over here? We have 1 minus sine squared. Is that equal to cosine squared? Well, yes, it is. 1 minus sine squared is cosine squared. So these were both Pythagorean identities. We use Pythagorean identities. From here, it looks like there was some distributing that happened, right? That's like the cosine squared was distributed backwards. That would give you cosine squared minus cosine to the fourth squared, cosine to the fourth. So that would just be, distributing would just be algebra. And that would be verifying of that proof. It is true that that proof is true. Let's do one more of these, a little more challenging. All right, we're starting with the original left-hand side. Tangent x times cosecant squared x minus 1 is equal to cotan x. To get from the first step to the second step, I noticed that this factor over here remains the same. However, tangent x turns into sine divided by cosine. That is one of our quotient identities. So if it's 1 over, that's a reciprocal identity. Then there's 2 quotient identities. One is tangent, one is cotangent. So boom, that right there. that is a dun, 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 quotient identity. Then it looks like this guy stays still. However, this guy turns into cotangent squared. Cosecant squared turns into cosecant squared minus 1 turns into cotangent squared. Cosecant squared minus 1 turns into cotangent squared. There's another Pythagorean identity. That was a Pythagorean. Sometimes students will get a little confused doing these and they will have trouble identifying which rule belongs to what line. So the idea is for this line, I'm saying what was done to get from here to here. So if this helps a little bit here, from here to here, that is right here. From this line to this line, whatever happened to get from that line to that line, that's what goes here. So what I'm writing down here is what the previous line to the line I'm on, what happened there. All right. The sine, cosine, they look like they stayed the same. It looks like here there was a change. So cotangent turned into cosine over sine. That is just a quotient identity. And then it looks like some simplifying happened. So there's a cosine on the bottom, so it gets rid of one of the cosines on top. There's a sine on top, it gets rid of one of the cosines on the bottom. And you're left with one cosine on top, one sine on the bottom. That is just algebra because we're not plugging in an identity, we're just canceling. And then turning cosine over sine into cotangent, that right there is a quotient identity. That's it. That's all there is here. So you're just identifying along the way what rule was used to prove an identity, to prove that tangent x times cosecant squared x minus 1 is equal to costan x. In our next videos, we're going to start actually proving trig identities. So I will see you then. Bye.